Good afternoon. Last time I showed you the implementation of a semaphore in the kernel. Now let's look how we can use the semaphore to synchronize the tasks. This is the implementation of a buffer. A buffer between writers or senders or producers and receivers or consumers. It is a cyclic buffer. That means that after the last element in the buffer, when we enter a new element, we start again from the beginning. So we do it in a loop. Okay, so it's a class with parameter being the size of the buffer. Mutex is a binary semaphore that protects the content of methods of this class from concurrent access. We can execute one method at a time. If another process wants to enter the method, it stops on mutex. Mutex is a shortcut of mutual exclusion. We have an array that is the body of the buffer, and processes enter elements to the buffer and retrieve elements from the buffer. We have two general semaphores, full and empty. Full protects processes from entering data more than capacity of them. So if the buffer is full, that is, if there are n elements in the buffer, this semaphore should be 0. And next attempt to write is suspended, is stopped. Empty acts symmetrically on the receiver side. This semaphore equal to 0 informs that the buffer is empty and we cannot retrieve anything from the buffer. So initially, full is n because we can add n elements before we will stop on this semaphore. Empty is initially 0. That means that we have no elements in the buffer. Mutex is initially 1, which denotes a critical section to be free, not occupied. And we have two counters that appoint an element in the buffer that is first free, so we can enter new elements to this index. And LOC is occupied. It means that it is the longest waiting element to be retrieved. And it is all about variables. Let's analyze put procedure. We close the critical section. We check if we can add an element to the buffer. If not, we wait until the receiver makes some room for new elements and executes V. Then we enter new elements to the buffer. We advance the index of an element to be entered. We inform the reader that there is one more element in the buffer. And we release the critical section. The get procedure is symmetric, so we need not analyze it in detail. Okay, there is a serious error in this solution. Could you tell me what is the error? Okay. Let us analyze the starting of the buffer. Empty is 0. And assume that a consumer starts to execute get operation. It closes the critical section and it wants to come through empty, but empty is 0, so it gets stuck at this position. And it waits until the sender will enter any element to the buffer. So, okay, the sender comes here, executes P of mutex, but mutex is 0 now because the reader previously closed the critical section. This situation is called deadlock. Consumer waits for a producer to enter an element, but the producer waits for the consumer to free the critical section, and they both wait. How to solve? We can swap those P operations. Now it's safe. It is not always so easy to recover system from deadlock. Do we need to swap V operations as well or not? Do we have to swap V operations as we swapped P operations? No, we don't. Because V operation does not halt any process. It does not stop a process. So V operations can be executed in arbitrary order. This is the definition of a deadlock. Some authors define deadlock for at least 2 processes, like in our example, but it can happen that one process falls into deadlock. For example, when a process initializes a semaphore with initial value 0 and executes P on this semaphore. is a situation in which a process or processes wait for conditions that could not be met. An example of using semaphores coming from Dijkstra papers is 5 philosophers. 5 philosophers are sitting on chairs at the table. There are 5 plates on the table and 5 forks between the plates. Each philosopher only eats and thinks. To eat, a philosopher needs 2 forks, left one and right one. So every fork is a shared resource between 2 philosophers. Here are the forks. Let's assume that philosophers start to operate, and each philosopher grabs his right-hand fork. And each philosopher wants to grab a left-hand fork, but it is occupied by the philosopher on the left. Symmetric situation if all philosophers grab their left-hand forks. And they want to take right-hand forks, but they cannot because they are occupied by right-hand philosopher. This causes a deadlock. Both situations are deadlocks. They will never eat. Let us imagine first solution to this problem. One philosopher out of 5 is a special philosopher. All philosophers take, for example, they take right-hand fork first, but this philosopher takes left-hand fork first. So it never happens that 5 philosophers grabbed left-hand forks or right-hand forks. It never happens. So the system is safe. However, this solution is not elegant. Because, of course, this problem, abstract problem, is a model of a situation that can happen in programming. So assuming that we have 5 programs to run that take some resources, modeled as forks, and we modify the source code of one of those programs to operate differently. Correct and elegant solution should be fully symmetric, that the code of every philosopher is exactly the same. This first solution we can generalize, saying that at least one philosopher takes left-hand fork first, and at least one philosopher takes his right-hand fork first, and the rest in arbitrary order. but at least one left and at least one 5. So there is no situation when 5 philosophers grabbed left-hand forks or 5 philosophers grabbed right-hand forks. So it's more flexible, but still with special properties of some philosophers. This is the solution in which those philosophers take right-hand fork first, and one of them left-hand fork first. This is possible situation. Those philosophers grabbed their right-hand forks. This one grabbed left-hand fork because it starts from the left. This did not grab any fork because they accidentally, they are grabbed already. So this fork can be taken by this or this philosopher. Everything is okay. Second is left for those 4 and right for this distinguished. So assume that this philosopher takes the fork and eats. Okay. It will release the forks, so those 2 forks will be on the table. So this one will grab the forks and eat. When it leaves, then this one, and the chain starts to eat. It's safe. Another situation is similar, but this one takes this fork. Okay, it eats, that then it releases the forks, this one takes, and so on. Oh, another situation. Okay. How can we generalize this solution with distinguished philosophers? We can prohibit the 5th philosopher from taking the one name fork dynamically. When 4 philosophers grab their left-hand forks, we prohibit the 5th one to do the same dynamically. But we don't know which 4 have grabbed forks dynamically, can say. So we have 2 policemen. The left policeman takes care about right hands of the philosophers, and the other one takes care about left hands of the philosophers. And they allow maximum 4 one name forks, left or right, to be grabbed. Let's observe how it runs. Its initial situation. Those 2 philosophers ask this policeman to take their right-hand forks. He increases the counter and says, okay. This philosopher wants to grab right-hand fork. Okay. The counter is free and the fork is grabbed. This philosopher wants to take right-hand fork. Okay. Counter is 4, it's the maximum value. And if this philosopher reports that he can take the fork. The policeman does not allow for this operation. So in this situation, this one can take this fork and when it wants to take left-hand fork, this policeman says, okay, increases the counter of left-hand fork grabbed, and the philosopher eats. And when he releases those forks, informs the policeman, and now the policeman allows this philosopher because the counter is free now. This one wants to take left-hand fork. He allows, so he eats, and it's okay. This was the second solution. It is elegant and with maximum parallelism, because those two policemen, we can say that they respond to the orders of philosophers fully in parallel. It can be run even at the same time. This philosopher wants left-hand fork, this philosopher wants right-hand fork, and they can order the forks in parallel. So this solution is good for distributed solutions because it is much parallelism in this solution. The third solution is not so parallel. It's less parallel. And it is based on grabbing two forks or none. For example, this philosopher can take forks, this one those forks, and they eat. This fork lies on the table. However, it cannot be taken because those two are grabbed, so those philosophers cannot take this fork. Let's look at example scenario. Those two philosophers take the forks and they eat. This one releases the philosopher, so this one can take. Okay. This they eat, this one releases forks, and this one can take. Okay, it takes. And they eat. It releases, so this one can take. This releases, so this one they can take. Do you see what happens? What happens? The philosopher on the top never eats. Is it deadlock? No. This is interesting. It's not a deadlock. However, one of the philosophers becomes so hungry that he dies without deadlock. This phenomenon is called starvation, and we define it in different way than deadlock. Starvation is a situation in which a condition for the process can be met, but it never happens. because of some dependencies between other processes. Now we see why there are 5 philosophers. Why? Because having 2, 3, 4 philosophers, we cannot achieve starvation. The possibility of starvation starts at 5 philosophers. That's why Dijkstra, who is the author of this problem, appointed the number of philosophers to 5. I will show you the code of the solution of the second solution. For this purpose, I need to number philosophers and forks somehow. So for philosopher I, his left-hand fork is number I, and right-hand fork is I plus. I plus I define as I plus 1 modulo 5. But it is shorter, so I will use I plus. This is the code. It is a class because we should program everything as a class, not just a random collection of variables, procedures, loops, and everything. It's an elegant solution using a class. And it is my requirement for you for the midterm test and exam that your every solution to synchronization problem must be a class. We have 5 semaphores being forks. And 2 policemen. Dijkstra called them butlers, but I think policeman is better name. But B4 is in honor for Dijkstra, for butler. And we have 2 procedures: take the forks and release the forks. I is the number of the philosopher. Select instruction is taken from Ada. I use this instruction because it contains undeterminism. When we have 2 guards that are true, the choice between them is non-deterministic. So we can choose the upper guard or lower guard as well. Under the guard, we have the code that asks left policeman, and if he allows, grab left-hand fork. Then we ask right policeman, and if he allows, we grab right-hand fork. Or reverse order. On release, we again choose non-deterministically. We release left-hand fork and inform left policeman about this fact. Then we release right-hand fork and inform right policeman that we released it, or reverse order. This is important. The policemen are initiated with value 4. So it is a counterpart to those counters. They are not strictly semaphores because they start from 0 and go to 4. But we implement it as semaphores that start from 4 and are decreased to 0, because in semaphores the synchronization condition is when the semaphore crosses the value of 0. So we initiate both policemen to 4, and every fork is initiated to 1, because initially it is 3. That's all. Excuse me. Let us return to our situation of a buffer with this error. Why did I put the synchronizing operations in that order? Because it is elegant and structural to encompass the entire method of the class with critical section from begin to end. And the scientists and designers tried to invent such a solution that would allow to declare a class and declare that this class is fully protected by critical region, like the synchronized qualifier in Java. In Java, when we use synchronized qualifier, the method of this class are protected by a critical section, just what we wanted. However, what to do with stopping a process inside the critical section? This was a serious problem, and the maybe more, but successfully 3 researchers invented similar constructs of monitor. They did it about 6 or 7 years after invention of semaphore. So it was not easy to define such a programming construct. What they invented? In a method, we declare the class as being protected by critical section, so the P operation on mutex and V on mutex are hidden in start and end of the method. They are hidden somehow. I have written P and V, but in fact, there are no such letters. We just add some qualifier to the class itself, like synchronized in Java. And the critical section lasts from begin to end in all methods of this class. And when the process stops inside the critical region, the critical section is interrupted. Waiting process does not occupy a critical section. It releases the critical section for the time of waiting. Opinions, if it should be done on V were different. Some researchers said that yes, some that not. So it is open question, and different realizations of monitor use different rules for V. This is on the left, this is the definition, abstract definition of a class, of a monitor. It is a class. The methods are protected by a critical section. Suspending a process inside a monitor releases the critical section for the time of waiting. And the critical section is passed from one process to another using immediate resumption in two versions of monitor by Hoare and Dijkstra. They are very similar, and we will not distinguish them. And quite different concept is in Brinhansen monitor, in which the process that signals other process does not lose the critical section. It is not so elegant solution. I don't like this version of monitor, but it is used in practice. These are marked with red the elements that do not occur in regular class. They occur only in monitor. So first is some qualifier. Those authors propose just to replace the keyword class with keyword monitor. Okay. Inside the monitor, we can declare special variables called conditions. Of course, it is somehow misleading because we have Boolean conditions. It's quite different issue. Boolean conditions are in the condition of conditional statement, for example. Condition variables are for stopping the processes. A process stops on condition variable with operation wait. And for the time of waiting, a process loses the critical section. So if a process cannot continue in the method, it unconditionally waits. The wait operation is unconditional. Here is the condition. But when we cross through then, it is unconditional. We cannot resign from waiting. And we release the critical section. So we let another process to enter some other method in which it changes variable that we can operate in our method. And this process should resume our process. So first we check if we can continue. If not, we wait. After that, we do what is needed. We modify the variables, those variables in the monitor. And finally, we check if a process waits for what we done. If yes, we resume this process. These are all the syntactic differences between a class and monitor. Just some qualifier of monitor, condition variables, and operations on them. Wait empty. Empty checks if there is a process waiting on condition variable. And signal. Oh. Okay. So the qualifier monitor protects every method with critical section from its begin to its end, with exception of time when the process waits, in which the critical section is released. Of course, when we signal a process in another method, this process should perform wait. It's no sense to signal a process that cannot wait. So it's CJ, you see, the same condition variables. This process cannot continue and waits. This one changes the variables in monitor and resumes this process. So we assume that there is in this monitor some signal for CI. It's no sense to wait when nobody can resume the process. There should be in some method the signal operation for CI. Here I showed the differences between monitor and semaphore. This is our monitor concept compared with semaphore in our buffer function. Monitor qualifier for the class adds critical section. So it is a counterpart of P of mutex and V of mutex in the beginning and end of a method in the class. This monitor corresponds to those two operations in the beginning and end. Checking if we can and waiting is compared with P operation. P operation is conditional inside. P stops the process if semaphore is more than 0. No, is 0. It stops the process if a semaphore is 0. It does not stop if it is greater than 0. So inside P, we have conditional operations. Here, the condition is pulled outside. It's the process of suspending, the operation of suspending a process is split to two operations, checking and suspending. And here we see what is better in monitor. In P, conditional is crossing 0, and no other condition can be used. Here we can use any Boolean condition, not only crossing 0, but by some variable. Do what is needed is a counterpart of modification of internal variables of the class. Checking if a process waits and resuming it are hidden in V. V is conditional as well. V says if a process waits, resume it, otherwise increase the variable. So it is split to explicit two operations. So let us look how we implement the same buffer using monitor. It's a monitor, not a class. It is a class, but with critical section. Instead of two semaphores, full and empty, we have conditions full and empty. Put operation. First, this conditional statement. If it's put, we must stop the process if buffer is full. In semaphores, the full semaphore had two purposes: stopping a process when the buffer is full and informing how many empty places are in the buffer. Simply, the semaphore full informed, the value of the semaphore informed about number of free places. Here we don't have counting semaphore, so we must count elements in the buffer manually. We have special additional variable counter, which informs how many elements are in the buffer, and here we increment it. This is the same as before. And here, if there is a reader that waits to be resumed, we resume it. So this abstract checking if I can continue is implemented by comparing counter of elements with maximum capacity. This is the wait operation. This is abstract on CI. Here we have specific condition on which we wait. It is C full. Here we done what we need to do. Checking emptiness is applied to empty because we can fulfill the condition for reader in putting. And the same condition variable is used in signaling operation. So here we have the full implementation of a buffer using a monitor. I think that it's nothing to discuss because we discussed all of those operations in this slide. The only thing that we should add is two variables that we had in semaphore solution: the index of element to be entered and index of element to be retrieved. Of course, here we have condition variables that should be initialized somehow. Of course, initialization of those variables is initializing to the state when no process waits on them, but we assume that it is done automatically. In monitor, every condition variable is initiated automatically when the monitor starts. We can implement every synchronization mechanism using any other synchronization mechanism. We can say that all synchronization mechanisms are equivalent. we cannot imagine a problem that can be solved using one mechanism and cannot using second. Of course, it could be that with one mechanism it is easier, using the second it is more complicated. Or it can happen that using one mechanism we use one instance of this mechanism, and using the second we need several instances, like in our example. But every problem that can be solved using any synchronization mechanism. It is the code of the monitor that implements a general semaphore with initial value. So it is monitor with initial value. It has condition variable, one condition variable, and value of the semaphore. Value is initiated to initial value in constructor of this class. Procedure P. If value is 0, then wait on this condition variable. Then decrease the value of the semaphore. Operation V, increase the value, and if a process waits for that, signal this process. And that's all. What is important? We can achieve the second instruction in the monitor, in the method, following one of two ways. One way, if value is greater than 0, this condition is false, and we go directly to decreasing. If the value is 0, it is true. We wait. It is true, so we wait, and finally we are resumed. So this beginning part of the method of the monitor causes that we can reach the second instruction going directly to this instruction when this value is not fulfilled, or waiting and being resumed if this condition is fulfilled. Let us return to our 5 philosopher problem. We will solve the third solution, taking 2 forks or none. And for this purpose, we need more indices. For the philosopher I, his left-hand fork is number I, right-hand fork is I plus, as before. Left to left is I minus. That is I minus 1 modulo 5. And right to R is I plus plus. It's I plus 2 modulo 5. So philosophers is a monitor now. Forks do not need to be semaphores, and we cannot declare a semaphore inside the monitor. The semantics of a semaphore inside the monitor is not defined. And of course, if we force to have a semaphore in monitor, we will deadlock on every P inside the monitor. So now forks are just Boolean variables. And we have 5 conditions. A condition for every philosopher. Take procedure. If fork and fork on the left and on the right are free, it's okay. So it's not, if not, we wait. If any of those forks is taken, 1 or 2, we wait. When we are resumed, or if we directly go here, we take the left-hand fork and right-hand fork. Release procedure. We release the left-hand fork and right-hand fork. We check if left to left is free. If so, we signal. Small explanation. I do not check if this process waits on condition variable. Instead, I assume that signaling an empty condition is empty. It is just to save the space on the slide. I could do that I check if someone waits on Si minus. If so, I resume. If right to right fork is free, I do the same with right-hand philosopher. This is something that looks strange and is crossed out. Here I check if the fork is free that I made free. I made the fork free, I plus, and here I check if it is free. It seems to be not reasonable. However, in signaling a process, I lose the critical section. So when I lost the critical section, this fork could be taken by another process. That's why after losing the critical section, when I want to signal second or third or fourth process, I must recheck the condition that I fulfilled. Otherwise, this condition could be stolen by a process. Because when I lose the critical section, I lose control over variables inside the monitor. And when I get again the critical section, the relations between variables could be other than I left them. That's why after losing the critical section, I recheck what I fulfilled. Initially, all forks are free. Okay. Again, let's look for this condition. From this statement to the next statement, I can go using 2 ways. First is when this condition is not fulfilled. when this condition is not fulfilled, it means that two forks are lying on a table. So I can grab them. If any of them is not lying on the table, I wait. Then I am resumed by a process that releases the forks. Let us look how a monitor can be implemented inside the kernel. No, not inside the kernel. Let me recall. No, this implementation is using semaphores, binary semaphores. Monitor. It is implemented by declaring a binary semaphore that will govern the critical section of the class. Condition variables. They are binary semaphores on which a process can hang up, but for the purpose of safe resuming, we need to know how many processes are suspended on given condition. So for every condition, we have a semaphore and a counter of processes. Entering the method of the class. It's executing P of mutex, of mutual exclusion semaphore. Waiting on a semaphore, on a condition, waiting on a condition. It's most complicated of all implementation rules. I increment the number of processes waiting on condition CI. I release the critical section of the monitor, and I unconditionally stop on CI. I told you that generally P is conditional. However, this semaphore is always zero. It never comes over zero. So this P is unconditional because this semaphore is always zero. And when the process is resumed, it decreases the number of processes waiting on condition CI. Checking for emptiness of a condition variable is just comparing counter to zero. Counter of processes waiting on CJ. Signaling condition CJ. It's V on CJ, so a process that waits on CJ is resumed. And the calling process cannot run in a parallel with the resumed process in the critical section. Only one of them can run. It's the definition of critical section that only one process can run. So I execute P to let him continue. I stop. This operation is called direct resumption. When the process not only releases the critical section when it signals a condition variable, it transfers its own critical section to the resumed process directly. It is very important. Otherwise, let us return to the example. If the process here, for example, signals other process, if direct resumption is not applied, another process that waits here can enter and consume the condition that is directed to process waiting on condition variable. So the process that signals not only releases the critical section, but it transfers the critical section directly to the resumed process. It is called direct resumption. And it's very important element of a monitor, of Hoare monitor and Dijkstra monitor, because in Bring-Hansen monitor, it is solved different way. The same situation is achieved other way, because in Bring-Hansen monitor, it is similar that resumed process gets the critical section, but not using direct resumption. Another mechanism is used. Okay, so this pair of operations is in fact direct resumption. I signal Cj, so I signal just the semaphore on which process waits on condition Cj. And not to proceed in parallel with this process, I stop on mutex. And finally, finishing the method is just V of M, releasing the mutex. And constructor, mutex is initiated to 1 because it's critical section. All condition semaphores are initiated to 0, and they are always 0. They never come over 0, because their purpose is to stop processes on them unconditionally. And counters of processes waiting on all condition variables are 0. So this was the implementation using binary semaphores. You see that we used n binary semaphores, that n is equal to number of conditions plus 1. Why plus 1? For mutex. And here we have the implementation of a monitor in microkernel. Here I explicitly, differently from the implementation of a semaphore, I explicitly stated where the scheduler is called in the kernel. It is important because here, for example, a process can get stuck on a condition variable and it cannot continue, so another process should continue. So I call the scheduler. And I marked the calls that are syscalls, because some procedures of monitor will be called from condition variable implementation internally in the kernel. Those two are syscalls. Okay. Monitor is now, it is a class because we have no internal synchronization in the kernel. We arrange the synchronization. So monitor is the name, and class is the qualifier. It is not monitor that uses monitor. It is a class. It has a process that occupies a critical section. It is active process in this monitor, and a set of processes that wait to enter the monitor. They just wait on begins of methods. Ready in monitor. It is the queue of processes. Operation P, begin P. So it is starting of executing a method of a monitor. I marked it begin P previously. And the parameter is number of the process that calls this operation. If active is not null, it means that critical section is occupied of this monitor. So if there is a process in monitor, the process that enters the monitor waits in ready queue. It applies for the critical section of the monitor here. Otherwise, active is null, so the process that entered this procedure takes the critical section. Active is this process. And we call the scheduler, as in every kernel operation. And with V, with number of process. We have a temporary variable because we will resume some process, so we must know the identifier of this process. So this is the purpose of PR0. If this queue is empty, then active is nobody. Critical section is just free when I leave the monitor. Otherwise, I take one of ready processes on the monitor. I proceed get, which takes one process from waiting on the monitor in the ready queue, and I assign active PR0, this one taken from the queue, and call the scheduler. Procedure or method wait. See, it is not a syscall. It will be called from the condition operation. Operation wait of process PR. It should release the critical section. So it is almost identical to this syscall. We check if there is a ready process. If so, we assign to active. If there is no process, sorry. If no process is ready, we release the critical section, it is free. Otherwise, we get one of waiting processes and assign to active. So it's identical, but not a syscall. It is a procedure called internally in the kernel. And transfer, the name says, it transfers critical section between one process and another process. There are two processes. This one occupies the critical section, and this one is resumed. So our process that transferred the critical section comes to ready. It applies for a critical section as every other process. And resumed process gets the critical section. And the constructor, critical section is initially free, and we initiate the ready queue. This is the part of implementation with two syscalls. Two syscalls, wait and signal, and two procedures called from condition variable implementation. So now let us switch to implementation of conditional variable. Condition. It's another class. It has a parameter in which monitor it is declared. It is very important for condition variable because operations on condition variable do something with critical region of the monitor. So we must know which monitor is the owner of this condition variable. We have the queue of processes suspended on this condition variable. Wait, it is a syscall. Wait on condition is a syscall. Process PR. We enter our process to suspend it on this condition variable and call operation wait in monitor, the operation that we discussed before a moment. Function empty that checks if the condition has some processes suspended on this variable. It is a syscall. It returns if the suspended queue is empty. And signal called by a process, this is temporary variable. If there are processes suspended on this condition variable, if there are some, I take one of them and transfer critical region to this process. This is transfer procedure that we discussed before a moment. So it is not a syscall, this is syscall. And this is a procedure called from implementation of condition variable. And initialization is initialization of suspended queue. I told you that a process that uses semaphores or monitors changes a state. In microkernel, it is just state ready or active because the scheduler takes care about those two states, and a form of suspension. If we have a process ready to enter the critical section of a monitor, but the critical section is occupied, from the perspective of the kernel, is suspended. If it is suspended on a condition, again it is suspended, but the reason is another. So we will discuss the states of process from the perspective of the synchronization mechanism, not from the perspective of the kernel. We have a semaphore, number I, semaphore Ci. When we do not touch a semaphore, we are in neutral state. When we execute P on this semaphore and its value is 0, we enter to suspend it on Si. If semaphore value is greater than 0, we continue simply. Underlined is invoked by other process. So P is invoked by the process that we mentioned. It is V called by another process in the system. It resumes the process. However, if there are more than one process suspended on the semaphore, one of them is resumed, other wait. Okay, now I want to discuss a state graph of a monitor, but I will not manage to do it in time. So I think that today I gave you many information which are not easy. So let us finish for today. Next lecture will be performed remotely on next Wednesday in the evening. It will be about 6 o'clock. I will send you a message. Of course, it will be recorded for those who cannot attend. It will be recorded as every lecture. Tuesday one is cancelled, yes. Thank you and goodbye.
Thank you, goodbye.